In this session, we're going to talk about representing symbols, pictures, sounds, and other human information using only binary numbers. Binary numbers can represent symbols, pictures, sounds, and other human data because the data are encoded for use within a computer, that is, encoded as binary numbers. Often the representation is approximate, but like with fractions, we can be arbitrarily precise in the approximation, although there are limitations of word sizes and so on. For example, it would be difficult to accomplish 70 bits of precision on a 64-bit computer. Encoding schemes depend on the fact that numbers can represent letters and other symbols. It might be something like 1 represents A, 2 represents B, on down to 26 represents Z. That isn't quite good enough, but we'll see some encoding schemes that are good enough. Many kinds of human expression are represented using symbols called graphemes. In Western languages, we need about 52 letter symbols, that is, the capital and lowercase letters. I said about because some languages have more than or fewer than 52 letters. The Gaelic language, Irish, has 18 letters. Swedish has 29. We need the 10-digit symbols 0 through 9. We need punctuation marks, and we might need some diacritical or accent marks. Coding schemes that represent both letters and numbers are called alphanumeric symbol sets. And it really is almost as simple as 1 represents A, 2 represents B. I used the word grapheme a moment ago. A grapheme is the smallest functional unit of a writing system. So for example, writing English, we use the Latin alphabet. The Latin small letter A is a grapheme. The Greek small alpha is a different grapheme. Those graphemes get expressed as glyphs. You can think of glyphs as the symbols within a font set. So that Latin small a could be an A with a hook, an A with a bar on the right side, or even the elaborate black letter Old English A. That's the same grapheme, but with different glyphs. You can think of the same grapheme expressed using different fonts. The Greek small alpha looks very much like a Latin A with a bar on the right. It's a similar glyph, but it's a different grapheme. One early encoding standard was ASCII, the American Standard Code for Information Interchange. It was standardized in 1963. It's a 7-bit encoding scheme because it was used for teletypewriter and telegraph transmission. Transmission time was expensive in 1963, and so the encoding scheme used the fewest bits possible to get us those upper and lowercase letters, numbers, symbols, and punctuation. We now store those ASCII characters in 8-bit bytes. We do that because modern general-purpose digital computers have byte-oriented addressing, and so the smallest addressable unit of memory is a byte. We'll stick 7 bits in there, and at least to begin with, have the most significant bit remain a 0. ASCII is still around since 1963. It is the first 128 code points of Unicode. We'll define code point and talk about Unicode a little later. We need to remind ourselves about binary numbers. How many unique combinations of n bits are there? 2 to the nth power. How high can we count in 8 bits? 0 to 2 to the n minus 1. So there are 2 to the n combinations. One of them is 0, and that means the largest number we can represent is 2 to the nth power minus 1. Notice that that minus 1 is not in the exponent. First you take 2 to the nth power, then subtract 1. If we think about ASCII, how many possible combinations are there of 7 bits? And the answer, of course, is 2 to the 7th power, which is 128. And that means that ASCII has 128 possible symbols. The ASCII character set includes 33 non-printing characters. Those are things like new line or return. The 26 uppercase Latin letters, 26 lowercase letters, 10 decimal digits, and 33 symbols and punctuation marks. If you add all those up, you get 128 or 2 to the 7th symbols. 0 is used for the null symbol. An ASCII reference table looks like this. Don't even think about memorizing this. This is something that you look up when you need it. The labels across the top represent the most significant hexadecimal digit in an ASCII character, and the labels along the left side represent the least significant digit. I've highlighted the letter small t. It is underneath the 7 in the column and in the row labeled 4, so that small t is a hexadecimal 7-4. If you look up at the upper left corner, the 00 symbol is the null symbol. An encoding scheme has a couple of characteristics that are important to how it can be used. One of them is the collating sequence or sort order. We want an ordering over a code set such that B is somehow greater than A so that we can sort things into alphabetical order. For a simple code set, we can choose a binary code for B that's larger than the code for A, and then just sort by numbers. However, we run into the complication of what to do with an uppercase A and a lowercase b. Is the lowercase b greater than the uppercase A? That's a decision that has to be made when the code set is designed. The other main characteristic is the size of the character set. We only have 2 to the nth combinations in n bits, and we'd like to keep the number of bits in each character, in each symbol, relatively small so they're easy to deal with. At this point, I need to talk for a minute about the difference between the symbol 1 and the number 1, the idea of 1. Symbols represent numbers. The idea of 1 is that mathematical abstraction that is unity. The symbol 1 represents the abstraction. To the computer, they do not need to be the same, and generally they are not the same. Other number symbols also represent abstractions, and like 1, the symbols and abstractions are not the same. Let's look at that in detail. The binary number 1 in 8 bits is 7 zeros and a 1. The ASCII code for the grapheme 1 is 0110001. They are not the same, and that is okay. 1 is an integer, and the symbol 1 is the code for a symbol or grapheme. ASCII is a 7-bit code, 128 combinations. Because of the byte addressability of modern computers, we store each ASCII character in 8 bits. How many combinations of 8 bits? 2 to the 8th, 256. Early on with computers in the United States, the remaining 128 combinations were used for line drawing characters, smiley faces, and things like that. That was a convention, not a standard. The standard was 7-bit ASCII. That extra bit, which generates 128 extra characters, extra code points, the extra bit was also used in other ways. The International Standards Organization ISO 8859 used the extra combinations for diacritical marks and symbols from other languages. Remember those 29 letters in the Swedish alphabet. ASCII is not the only possible encoding scheme. We're going to look at another one in just a minute, but there are many possible encoding schemes. I just mentioned ISO 8859. For historical purposes, I need to mention EBCDIC, the Extended Binary Coded Decimal Interchange Code. That was invented by IBM, independent of ASCII, and used in IBM mainframe computers. You might still find some EBCDIC files around somewhere. Translation to and from ASCII is possible, but not easy, because EBCDIC is an 8-bit code, and so there are 256 characters, not 128. All of this worked pretty well when computers were being made in the United States and the United Kingdom. The problem is that there are lots of other languages, and many of them don't even use the Latin alphabet. Cyrillic, Greek, and Hebrew, for example, do not use the Latin alphabet. Hindi does not use the Latin alphabet. Farsi does not use the Latin alphabet. There are also non-alphabetic languages, like traditional Chinese, that use a large set of symbols for words and ideas, rather than for letters. Those symbols are called ideographs. ASCII with line drawing faces was fine in the United States in the 1980s. It didn't work for Western European languages, and it didn't really work anywhere else. One idea, and this is the thing that got us ISO 8859, was instead of line drawing characters and smiley faces, make the first 128 characters still be the same as ASCII, but use the remaining 128 characters for things like an O with an umlaut, an A with an acute accent, the Swedish OA letter, or N with a cedilla. If we do that, we can cover a lot of European languages. There wasn't just one of those. There were several mappings of codes to graphemes. And each of those mappings defined something that was called a code page. The code page was nothing more than the list of mappings for a particular file of data. The problem is that text created with one code page was garbled if displayed under another. We use the Japanese word mojibaki to describe such garbled data. That means programs have to know which code page to use, and the data might not, in fact probably isn't, tagged with the code page that was used to create it. Even worse, with 8-bit code pages, we're still limited to 256 characters, and that's not enough for many languages. One possible solution is to use more bits. ASCII 7 bits, 128 symbols, 8-bit byte addressable computers, including the ISO 8859 code set. We got 256 symbols. If I use 2 bytes, 16 bits, I get 65,536 symbols. But if I were going to cover all the world's languages, I would need over 200,000 symbols. So in the early 1990s, a couple of folks in different places came up with the idea of a single coding scheme, one code to rule them all, that represents all possible characters in all the world's languages. That would be, as we said, over 200,000 symbols. This code set would also be able to represent dead languages, things like cuneiform, which is Sumero-Akkadian, medieval languages, and everything. That would take about 18 bits per character. That's a distinctly odd number for byte-oriented computers, and so some compromise was necessary. The winner of those several development programs was something that is now called Unicode. Unicode maps numbers, and we call those numbers code points, to graphemes. When we talk about a Unicode code point, it is a particular number assigned to a particular grapheme, almost exactly like the number 1 is assigned to the letter A. They didn't assign 1 to A, but it's exactly the same principle. The first 128 code points of Unicode correspond exactly to US ASCII. The great advantage of that is if I have a file of data encoded in US ASCII, it is already magically in Unicode. A whole lot of data that was sitting around in ASCII suddenly became sitting around in Unicode. They went further. The first 256 points correspond to ISO 8859. Remember, in ISO 8859, the first 128 code points were ASCII. The next 128 were used to encode things like that Swedish OA letter. That's Unicode. Code points are numbers assigned to graphemes. A Unicode transformation format describes how those numbers will be represented in computer storage. Unicode is just numbers. The transformation format describes how those numbers are stored. One of the first transformation formats was something called UCS2, Unicode Character Set 2. 16 bits per character, 65,536 to the 16th symbols. We got a whole bunch of alphabets out of that, many but not all of the ideographs from the non-alphabetic languages. And 16-bit Unicode included escape sequences that could say another 16 bits is coming. And that means we could use up to 32 bits to represent some characters. Because the first 16 bits were an escape sequence, we still didn't get enough values for 200,000 symbols, not enough to fully cover the world's languages, and worse than that, we needed at least 2 bytes for every character. Nobody was very happy with UCS2. Americans, both North and South, and most Europeans were mostly okay because UCS2 handled their living languages easily. It still took 2 bytes for every character, though. Places like India and China were not so happy. And so the Unicode folks invented planes. The basic multilingual plane is that original 16 bits, 65,536 code points. Then they invented a supplemental multilingual plane and 14 more. These multilingual planes sound a lot like code pages, but they're different in that a code page mapped a symbol to one of 256 characters. In the Unicode planes, each code point has a distinct number. So we're not using the same number over and over again with different code pages. We have distinct numbers for each grapheme represented in Unicode. But we're still stuck with those 16-bit characters. Some folks working on that had the idea that, I can encode ASCII in 7 bits with a leading 0. With an 8-bit byte, I can use that extra bit to say more is coming, and I can get a variable length code. The variable length codes in Unicode, and we're talking about UTF-8, the Unicode transformation format for 8 bits. Those variable length codes had leading bytes and continuation bytes. Each code point had a leading byte, and they might have 1 or more continuation bytes. It is set up like this. For the first 128 code points, there's only a leading byte. It is a 0 followed by 7 bits of US ASCII, essentially. If we need more bits, the leading byte's number of leading ones tells how many total bytes in the character. So if you look at the second line in the table, I have a 110, 2 leading ones. That means I'm going to have 2 bytes in the character. Continuation bytes always start with 10 and then have 6 data bytes. If I need 16 bits, that's going to take 3 bytes instead of 2, but the leading byte is a 1110 and then 2 trailing bytes. That gives me 16 bits of data. I can get 21 bits of data, enough to enumerate over 2 million things with a 11110 leading byte and 3 trailing bytes. Now I was asked why we didn't just use a 1 as the first leading byte. The answer is that with the coding scheme that's in that table, and I'll talk about it some more in just a minute, it's never possible to confuse a leading byte with a continuation byte. All 2 to the 20th Unicode characters can be represented, and in fact there's room for another 2 to the 20th. Frequently used characters take 1 or 2 bytes. If something is encoded in plain old ASCII from 1963, it only takes 1 byte. Many of the characters that are frequently used take only 2 bytes. UTF-8 is self-synchronizing. Leading bytes have only 4 possibilities: 0, 110, 1110, or 11110. The number of ones indicates the total number of bytes, except when there is only a leading 0. Continuation bytes always start with 10, and because of the way the leading bytes work, they can never start with 10. It's easy to recognize UTF strings, and getting multiple alphabets in one document is really easy. If you look at the textbook, I used the word mojibaki and I transliterated it into Latin characters in the text, but you can read it in Japanese in the footnote. That was easy to do because the textbook is composed using UTF-8. UTF-8 is not perfect. It's hard to find the nth character of a string. Also, Microsoft standardized on UCS2 early on and didn't get around to UTF-8 until Windows XP, which is quite late in the scheme of things. The Indians and the Chinese are still not happy because it can now take as many as 4 bytes to encode a character, and there are a lot of Indians and Chinese. So we talked a few minutes ago about the difference between the number 1 and the symbol 1. Using ASCII, the letter A is 01000001, if I got enough zeros in there. 01000001 base 2 is also 65 base 10. So the same string of bits can represent either the Latin uppercase A or the decimal number 65. How does the computer know whether it's an A or a 65? Context. The programmer must keep track of whether binary data represents letters, numbers, sounds, pictures, or something else. It's not as hard as it sounds. Keyboard data represents encoded symbols, scanner data and camera data represent images, microphone data represents sounds, and so on. In modern languages like Java, the programmer can establish context by declaring the data type of each item. So with all of that done, let's look at data input. We always start with data in human form. In the slide we have some music notes. There is an input device, and we end up with a string of bits representing that data in a form that can be used by a computer. Some of those input devices are digital devices, like a keyboard. Those digital devices generate binary data directly. So typing on a keyboard produces binary codes for each of the key presses. It doesn't really produce UTF-8, though. Pressing a key generates a digital signal equivalent to a binary number. That's called a scan code. It's not yet encoded in a scheme like UTF-8. Releasing the key generates another scan code. And that is what makes key chords like Control-Alt-Delete possible. That's also what makes control sequences like Control-A, and what makes repeating characters possible. The operating system sees the scan code when the key is depressed, a different scan code when the key is released. And so if you're holding a key down, the operating system doesn't see the release code, and it can start repeating that character. Translation to UTF-8 or something else comes later. There are other ways to get alphanumeric input. Optical character recognition is one, barcodes another, magnetic stripe devices yet another. These are input mechanisms, but in another sense they're also storage. I've used the word analog a couple of times without really defining it. Analog devices produce analog signals. An analog signal is continuously varying data in which an electrical signal is analogous to a physical quantity like a sound. So the diagram, the sketch on the slide, we have sounds, music, a microphone, and something that looks like a waveform. Okay, the sounds, music, speech, whatever, generate pressure waves in the air. The microphone picks up the pressure waves and generates an electrical signal that is analogous to those pressure waves. And that's where the word analog comes from. Analog input requires special hardware. That hardware is an encoder that converts the analog signal to a digital signal. Conversion is approximate, and we'll talk about how that conversion works with sounds in just a little bit. Let's think about pictures first. If you look closely at a computer screen, you'll see that the image is composed of many tiny colored dots. Photographs are also composed of many tiny dots, and so are printed pictures. In photographs, those dots, they're called film grain, may be too small to distinguish without a microscope. Generally, you can see the dots in printed pictures, and you can see them in computer pictures if you look closely. Each of those dots is called a picture element or pixel. You might see the word PEL, P-E-L, used to represent picture element as well. The number of pixels per unit of distance, inches or millimeters, determines the resolution or fineness of the picture. There's an example coming up. More resolution, more pixels per inch is better. The number of bits per pixel determines the color depth, that is, the number of colors that can be displayed, and once again, more is better. And each pixel is stored as one or more binary numbers. So here's that example of resolution that I promised you. On the left, you have a low resolution image. The pixels are big, and there are not very many of them per inch. On the right, higher resolution, the pixels are much smaller, and in fact, you'd have to get really close to the screen to distinguish them. To get photorealistic images, like the one on the right, the pixels must be too small for the eye to distinguish individual pixels. Apple's Retina display uses roughly 350 pixels per inch, and at a normal viewing distance, they are too small for you to pick out the individual pixels. The idea behind the name Retina display is your eye believes that it's seeing a continuous color. So that's resolution. Color depth, the number of bits per pixel. I can have an 8-bit color depth, like the example on the left, and that means I'm limited to 256 colors. That works just fine for comics and line art. With 24 bits, I can get 16.7 million colors, and there's an example of that on the right. The human eye can distinguish more than 16.7 million colors, particularly in shades of green. 16.7 million is enough to give us photorealistic images. How does that work? The RGB, red, green, blue color model uses additive colors. Computer displays emit light, And we can use the concept of additive colors, making many colors from the three primary colors, red, green, and blue. So as you can see on the slide, red and blue together make magenta, red and green together make yellow, green and blue make cyan, that kind of turquoise color, and all three together in equal proportion give us white or a shade of gray. By varying the proportions of each of red, green, and blue, 8 bits each for red, green, and blue, 24 bits for each pixel, I can get all 16.7 million colors. Printing turns out to be a lot harder. Computer displays are illuminated, the colors are additive. Printed colors are reflected, so light hits the printed page and is reflected. Printing uses the secondary colors cyan, magenta, and yellow. Those are the ones that were the combinations of red, green, and blue in the RGB model. This color model is called the CMYK model. That K stands for black. We already used B for blue in the RGB model. We need black because mixing cyan, magenta, and yellow doesn't give us a true black. It gives something that's kind of a muddy brown. Printed colors are subtractive. And we can see that by looking here and seeing that cyan reflects blue and green, but absorbs red. Magenta reflects red and blue, but absorbs green. If I combine cyan and magenta in equal amounts, I get blue. I can combine magenta and yellow to get red, cyan and yellow to get green, and I'm going to use a separate black ink to get black. Better color depth means more bits per pixel. Higher resolution means more pixels per inch. So more pixels and more bits in each one. Better pictures mean lots of bits. High-resolution photorealistic images are big. There are several image formats. The GIF format, and yes, it's pronounced like the brand of peanut butter. I know this because the people who invented it said so. The GIF format was invented by CompuServe in 1987. It uses an 8-bit color palette, so you can pick any 256 colors you want, but you only get 256 colors. The GIF format is quite good for line drawings and artwork that has large areas of color. The JPEG format is named for the Joint Photographic Experts Group, who designed a compression algorithm based on the way the human eye perceives data. And so it's good for photographs. In large areas of a single color, you can get compression artifacts, and I'll show you what that looks like in just a minute. A somewhat new color is PNG, the Portable Network Graphics format, which is intended to replace both GIF and JPEG, but hasn't really made the kind of inroads that its inventors thought that it might. So let's look at a comparison of GIF and JPEG. At the top left, we have a GIF image. It's 14K. If I convert it to JPEG, I can get it compressed down to 5K bytes. But if you look at that area that's kind of not quite turquoise, suddenly all the lines that touch it have rough edges. Those are compression artifacts, and they are the result of the compression algorithm in JPEG. Now, I had to compress it quite a lot to get those artifacts to show up. If you compress less, you will have fewer compression artifacts. At the lower left, we have a 27K byte GIF image of a photograph. At the lower right, there's the same photograph in JPEG. It's only 8K, and it actually looks a little better because there are more colors available. GIF, JPEG, and PNG are raster images or bitmap images. That means that they're composed of row after row of pixels. And if you look closely at the screen, you can see that. There are other bitmap formats, but the bitmap or raster image format is not the only kind of format. Another kind of format is the vector image format. Geometric objects can be described mathematically. So the image that you see is described with circles, segments of circles, and line segments only. That's all that's on there. Circles, circle segments, line segments. I can describe a circle with center, radius, and line width. I can describe a line with its two endpoints and line width. If I need color, I have to add that in too. I can get much more compact storage than with a bitmap, but I'm not getting a free lunch. I end up using more computation, both to generate and to store those vector images. The vector image format that you're most likely to have run into is SVG, Scalable Vector Graphics. Vector images need to be converted to bitmaps for display, and that requires even more computational resources. This thing called an object image extends the idea of vector images, and we get pictures of ogres, I guess. Now, nobody knows what an ogre is supposed to look like, so I guess that's it, huh? But if you look at the grass, at the trees in the background, at the fabric in the ogre's clothes, we have extremely realistic images. Until last year or this, it was very difficult to make images of human faces. They were kind of creepy because people had not learned how to capture all of the information necessary to make a realistic human face. These object images are mathematical models. They never exist in real life. Not photographs, not paintings, not anything like that. Movies, some movies, but particularly Shrek and Toy Story, were made entirely from object images. Speaking of movies, how do we do moving pictures, video? If I can change an image 15 to 30 times a second, I can trick the eye into thinking that it's seeing motion. Back when motion pictures were on film, the films were displayed at 24 frames per second, and the image on the slide is a piece of motion picture film. That's about 41 milliseconds. Each of those frames is slightly different from the one before it, and together they trick us into thinking that we are seeing motion. Each frame is just a raster image, but they're big, and we need up to 30 or even more of them a second. So we might need as much as 27 megabytes of data every second to display moving images. Data can be compressed, so we trade less data storage for the need for more computing power to decompress the data. The WebM format, which we haven't really talked about, but which was introduced by Google a few years ago, requires a fair amount of work to compress, but is easy to decompress. Google's idea in inventing WebM was to make it easy to decompress moving images on relatively low-powered mobile devices like phones and tablets. I told you we'd get back to sounds, and the time has come. Sound is inherently analog, that is continuous, and continuous in two dimensions: amplitude, that is loudness, and frequency, that is pitch. Amplitude and frequency can vary independently of each other. So if we look at something that might be a sound wave if viewed on an oscilloscope, and this is just a couple of cycles of that sound wave, the frequency is the distance between peaks in time, and the amplitude is the height from the lowest valley to the highest peak. Audio gets encoded as a series of integer samples, that is, a series of numbers. digital values, digital signals. The integer value determines the amplitude. An integer of large value, that's a loud sound. An integer of small value, that is a soft sound. The sampling rate determines the maximum frequency. If we look, here's a piece of a sine wave. The gray bars show where samples are taken, and the blue stair-step line represents the digital signal that was stored. So neither the samples nor the interpolation between the samples is exact. The sampling rate determines how far apart those gray bars are, and the size of the integer sample determines how many divisions we get in that stair-step. So let's look at a little bit of theory. Nyquist's sampling theorem says that we must sample at twice the maximum frequency we want to reproduce. That's a theoretical minimum, so actually we sample at higher rates than that. And I'll give you an example in just a minute. Frequencies get expressed in hertz, abbreviated Hz, and strictly speaking, hertz is 1 over time, but it's easiest to think of as cycles per second. That middle A, the tuning fork A, is a 440 hertz sound. Young folks can hear up to about 20,000 hertz. I can't anymore. I used to be able to, but I listened to very loud music when I was about your age, and now my high-frequency hearing is shot. But you can still hear up to about 20,000 hertz. In order to reproduce that, we'd have to sample at 40,000 hertz or more. And as it turns out, compact discs use a sampling rate of 44,100 hertz, just a little more than the theoretic minimum of 40,000 hertz. How many bits in the sample? More bits provide better discrimination among amplitudes and a way to get rid of some noise. With telephones, we need quality only good enough to let us be able to recognize voices. It turns out that 8-bit samples, integer values 0 to 255, are good enough for recognizing voices. We don't need anything of higher quality. We'll talk about the sampling rate in just a moment. Compact discs, 16 bits for each of 2 stereo channels, so 0 to 65,535. I can have 65,536 steps and 32 bits per sample, 16 bits for each channel. Telephone, 8,000 samples per second, and where that came from is that the human voice is in the few hundred to about 4,000 hertz range, unless you're a soprano and really reaching for it. And so if I can reproduce 4,000 hertz, people can recognize voices. That means I have to sample at 8,000 hertz, 8,000 8-bit samples every second. That is 64,000 bits per second, and that's good enough for recognizing voices. I've mentioned that CDs sample at 44,100 samples per second. There's 2 channels, so 32 bits for each sample. 44,100 times 32 is 1,411,200 bits per second. A lot of data. The trade-off, no such thing as a free lunch. If I want higher quality sound, I need more data. High quality means big files, whether it's pictures, sound, or video. But in some pictures, there are large areas of the same color. There's silence in some parts of an audio recording. Compression can recode data to take less space. Lossless compression is a compression algorithm that allows the original signal to be recovered exactly. So think about compressing data files. You use maybe the zip algorithm. It is lossless because you want to be able to unzip that data file and get back exactly what was compressed in there. In lossy compression, the original signal is only approximated when it's decompressed. And we can get away with that with a whole lot of what we do with multimedia. Compressing audio, we do both lossy and lossless compression. The first thing to do is to discard all of those frequencies that the human ear can't hear. That's lossy compression. I've thrown away everything that is above about 22,000 hertz. I compress what's left using an algorithm called Huffman coding, which is a lossless compression algorithm. Are we going to go into the details of these algorithms? No, thank you. I took a multimedia course in my doctoral program, and compression algorithms just about killed me. How do we get data in? Well, we've looked at some examples as we've gone through. Images come in from scanners or digital cameras or digital video. Sounds come in from microphones and codecs. Video comes from cameras or other image generation, and video codecs. Plenty of ways to get multimedia information in. So that's it. I hope you have found that the time it took for me to re-record this was worth it.